So finally, what we can do with gas laws is to put everything together. We're talking about Boyle's law, Charles' law, Gay-Lussac law, Avogadro's law. We put all of them together into what's known as the ideal gas law. So if we recall, we know that volume is proportional to the number of moles. It's directly proportional to the temperature, and it's proportional to 1 over the pressure. We can start to combine this and say that the volume is proportional to the number of moles times the temperature over the pressure. And then if we put in a constant, we can say that the volume is equal to some constant, which in this case we're going to call R, times N times T over P. Now it turns out this constant R is known as the ideal gas constant, and is the same for any ideal gas. So what is an ideal gas? Well, basically an ideal gas is any gas that follows the ideal gas law. And so if we rearrange this equation, we get it in the form that we most commonly see, which is PV equals nRT, where R is equal to 0.08206 liters atmospheres over moles times Kelvin. So one consequence that this does have is, unlike all of our other gas laws where we said you can use any volume unit as long as it's the same on both sides, in the ideal gas law, if you're using this value for R, which is the most common value for R, then your units have to be liters, atmospheres, moles, Kelvin. Now, what happens if a gas is not an ideal gas, or it doesn't follow the ideal gas law? Then what do we do with it? So there's another equation known as the van der Waals equation. You won't need to know that for this course, but just to show you what it is here, this is known as the van der Waals equation. The van der Waals equation, you'll see, is fairly similar to the ideal gas law. In fact, the entire right side is the same, nRT, but we can see there's an adjustment to the volume piece based on the number of moles and a constant B, which is dependent on the gas, as well as an adjustment to the pressure. But again, we're not really going to concern ourselves with this difference in this course. So basically, you can take the ideal gas law, and if you know 3 of the 4 terms, because R is a constant, you can solve for the other one. But in addition to that, you could also use the ideal gas law to find the mass of a gas. You could use it to find the molar mass, or even the density. How would we do those? Well, the mass is probably the easiest. So let's start with that. So here we've got some sample of argon. It has a volume that's given, as well as a temperature and a pressure. But we're not looking for number of moles here. we're looking for mass, or how many grams of argon are present. And if we look at our gas law, PV equals nRT, mass doesn't appear in this gas law. So how do we find that? Well, if we think about it, one of our terms, number of moles, if we know the number of moles, we can use that to directly calculate the mass. So what this really is a question where we're going to solve for number of moles and then use that to find the mass. But in addition, we have some conversions we have to do. Remembering the value of our constant, R. We know our units for pressure have to be atmospheres, so we convert that. And we know our temperature, as always, has to be in Kelvin. All right, so once we've done those conversions, we can take our ideal gas law, and given that we're solving for number of moles, we can rearrange it to get N is equal to PV over RT. From here, we can just plug the values in. Notice we didn't need to convert our volume, that was already in liters. And our temperature, which we converted to Kelvin. And so we calculate here that we have 0.782 moles of argon. So how do we convert that now to grams? Well, we just use the molar mass, as we learned a couple chapters ago. So we get out our periodic table. We find that the molar mass of argon is 40 grams of argon is 1 mole of argon. And so we get 31.2 grams. So that's how we could use one of our gas laws to determine mass. It's just a matter of getting to number of moles and then using moles to calculate mass. What if we wanted to calculate molar mass? Let's try one like that. So here, we're trying to determine the molar mass. And what information do we have? We have volume, we have the mass, we have temperature, and we have pressure. So our pressure is 775 millimeters of mercury. Now, assuming we're using the ideal gas law, we can't have this in millimeters of mercury. We have to convert to atmospheres. This converts to 1.02 atmospheres. The volume is 125 milliliters. Have to convert that to liters. Again, we have to do these conversions here so that our units that we're working with match the units of the ideal gas constant. What's the number of moles? Well, we don't know that. We're given the mass, but because we don't know what gas this is, we can't use that to calculate moles. And the temperature here is 298 Kelvin. Now, what is molar mass? Well, molar mass is the mass of something per mole. So if you know the mass of an object and you know how many moles you have, you can use that to calculate its molar mass. So the one we don't know in this equation is our number of moles. We already know the mass. So if we can put those together, solve for moles, use the mass that we already have given to us, we can calculate the molar mass. So again, ideal gas law, PV equals nRT. Pressure, we just plug our values in. And we ran out of room here a little bit, so this is where our temperature goes, 298 Kelvin. If we solve for N, we find that we have 0.00521 moles. So now we can find our molar mass as the mass that we had, 0.23 grams, over the number of moles that we just calculated, and we get a molar mass of 44.1 grams per mole. So that's how we do that. All right, final question. What about density? So let's say we had a sample of carbon dioxide. So I want you to find the density of carbon dioxide at 25 degrees Celsius and 735 torr. What's our first step? Convert. So 25 degrees Celsius is 298.15 Kelvin, and 735 torr will convert to 0.967 atmospheres.
Okay.
That we can finish up here. to calculate our density of 1.74 grams per liter. So I may have accidentally had my mic muted there for a moment, so let me just go back through that. We converted our temperature to Kelvin, our pressure to atmospheres. Knowing that moles are equal to mass divided by molar mass, I substituted that into moles in our ideal gas law. So this is mass and the bottom is molar mass. We then rearranged the equation to solve for mass over volume, and we found that mass over volume, which is the definition of density, is equal to pressure times molar mass over R times T, and that gave us this equation, which we solved for the density. So at this point, you should go and do some practice problems dealing with the ideal gas law. That's the next in-class exercise, and in the next video, we'll go over those solutions.